Welcome to the MOOCs course Mechanical Unit Operations. This is the continuation lecture of our previous lecture, that is design of thickeners we are discussing. The title of this lecture is Gravity Sedimentation Design of Thickeners Part 2. Design of thickeners, since it is a continuation of our previous lecture, let us see what we have seen in the previous lecture related to the design part of the thickeners. Okay. So, thickener design is based on identifying concentration of the layer having the lowest capacity for passage of solids through it under operating conditions. The thickener design calculation, whatever we started with in previous lecture, we started with identifying a kind of layer which is having the lowest capacity for passage of solids through it, and then that layer is initially assumed to be at the bottom of the thickener, and then it gradually moves up with a kind of velocity VL bar, and then after that what we have found the concentration of solids in that particular layer which is moving up, and then what is the settling velocity of the particles that are passing through this limiting layer. Okay. This layer we identified it as a kind of rate limiting layer, and then according to this method sufficient area must be provided to ensure that the specified solid flux does not exceed capacity of this rate limiting layer. So, from this what we understand, actually whatever the area or expression for area calculation for a given thickener that we are going to develop, that is based on a kind of solids flux. There will be a kind of a layer which is having a kind of a lowest solid flux, and then corresponding to that we have to find out the area requirement for the thickener design, and then that area is going to be minimum area requirement. Okay. And then what we have done a kind of a material balance. Then we have found that the CL or the concentration solids in that rate limiting layer is nothing but C naught Z naught by ZL plus VL theta L. This C naught is nothing but the concentration of solids in the initial slurry, Z naught is the initial interface height, ZL is nothing but the height of that layer. Interface height when this CL or when this rate limiting layer has been identified, okay, at that particular time theta L. Let us say at settling time theta L, or sedimentation time theta L, the concentration of solids in that particular layer at theta L time is nothing but the CL, and then corresponding interface height is ZL, right, and then this ZI is nothing but the intercept, it is not the interface height. So, what we have these curves like this, sedimentation curve, that interface height Z versus theta, if you plot you will get curve like this. The interface height gradually decreases as particles settling down with respect to the time of sedimentation process, right. So, now let us say if this is time theta L, right, at this theta L, right, whatever the interface height is there, that is nothing but ZL, okay. Okay. But what is ZI? So, at this interface if you draw a kind of tangent like this, right. So, whatever this tangent at theta is equals to theta L that has been drawn on this curve. So, that tangent may be intercepting this y axis at some location, that intercept is ZI. That ZI is nothing but ZL plus theta L VL. VL is nothing but the settling velocity of the particles that is passing through this layer, okay. Or that settling velocity you can simply find it out, VL is equals to minus dz by d theta, simply minus dz by d theta if you do, you will get the VL, the settling velocity of the particle at time theta L here, right. So, that we can find it out from here, ZI minus ZL, and then this time theta L. So, actually that ZI information, whatever ZI is equals to VL theta L plus ZL information is there, that is coming from this slope at this point, okay. So, that is what we get, this, and ZI is intercept at theta L, and then VL is nothing but the slope of the tangent at theta L, okay. And then finally, we after doing a few more simplification, what we understand that CL ZI is equals to C naught Z naught, right. Now, Cl is the concentration of solids of that layer, rate limiting layer, and Zi is intercept as shown here, okay, and C naught is initial solids concentration, Z naught is initial interface height. Let us say if this is the initial interface height, that must be Z naught kind of thing. Okay. And then for several arbitrary thetas, the slope of the tangent and its intercept at theta is equals to 0 are determined from Z versus theta plot. Those are used for thickener area calculations. Okay. Till this point we have already seen in the previous lecture. Now, what we understand from here? So, the solids flux, right, solids flux does not exceed the capacity of rate limiting layer. So, what does it mean? So, if what we do, if we find out somehow the flux, solid flux F, and then plot it against the concentration, solids concentration of this layer at different times, that C, if you plot it, right, then you may be having a kind of layer or location where the flux is a kind of minimum one, right. The flux is a kind of minimum one, and then corresponding to that minimum flux, whatever the FL is there, that you can note down, and then from there we can get the required area for thickener. So, that is what we are going to do now. So, thickener area. So, required thickener area is fixed by the layer requiring the maximum area to pass a unit quantity of solids. Therefore, it is necessary to determine the concentration of such layer. So, we need to know what is Cl. What is Cl? We graphically we can know, and then also we already know it as a Cl is equals to C naught Z naught by Zi, that we have already obtained. Okay. So, but is that information is sufficient? Not at all. So, we need more information. We need to know the solids flux. We need to know the solid flux with respect to the concentration for different time intervals, right. So, once we have that one, from there we can get the required area for the design of the thickener. Okay. Till now what we have found? We have found only the concentration of solids of that rate limiting layer, and then settling velocity of the solids that are passing through this rate limiting layer VL, that is Cl and VL, that we have found as function of Zi. From here also we found that the settling velocity of the particle is function of concentration, right, is function of concentration. That is what we understand from previous derivations anyway, the previous slide that we have seen. Okay. So, now consider sedimentation, in which the total flux of solids is the sum of the flux of settling particles and flux to provide bulk flow of underflow. Let us say what we have a kind of continuous thickness, something like this. Once the steady state is achieved, these layers, different zones, A zone, C zone, B zone, D zone, etc. are there. So, these layers will be developed, right. A zone is a clear liquid zone, and then that is taken as a kind of overflow. D zone is a kind of a concentrated sludge zone from where you collect a kind of solids out, solids discharge you take, and then feed is coming with somewhere in let us say the middle of this sedimentation tank, right. Once the steady state is established, whatever the feed rate is coming, at that feed rate is equal to the whatever the overflow rate is going out and whatever the solids are going out. So, that these layers, whatever the layers are developed, right, different ABCD zones are formed, they are not disturbed, they are not disturbed. So, that condition we know as a kind of a steady state condition, that we know. So, now what happens from each layer? Let us say A is almost a kind of clarified liquid. From each layer, B is a kind of having some solids of concentration same as initial uniform concentration C naught, and then C is a kind of a transition zone kind of thing, it is having a different concentration. So, from each layer solids are continuously settling and then going towards the bottom zone, that is the D zone, where the sludge is being collected from where, right. So, now when the solids are settling, so there is a kind of a batch sedimentation of these solids because of the settling velocity of these particles, right. There is a flux, one flux is there, flux for the solids is there because of the settling of this particle. Another flux is there, the solids being discharged, taken out continuously from the bottom through the underflow discharge. So, there is a kind of solid flux here also, right. So, the overall solid flux of the system, this sedimentation experiment, if you wanted to get, you have to obtain these two information and then add them together, so that you can have a kind of total flux. F is equals to Fb plus Fu is equals to, Fb is nothing but Cv plus Lu C by A. Let us say if you are obtaining flux at time theta 1, so then it should be C1 V1 plus Lu C1 by A, like that. Okay. If you are obtaining the flux at theta is equals to 2, because now the solids are continuously settling until a kind of final total or almost complete sedimentation is taken over. Until that point, solids are continuously settling, and then at each layer, different times the solid flux are different, right. So, this solid flux, if you calculate at different times, so then you can have a kind of F versus concentration information, because the concentration of this layer is also changing with the time, right. So, initially let us say all the solids concentration everywhere uniform, that is C naught concentration was there before the sedimentation starts. So, later on what happens, gradually the concentration of solids in A is almost negligible or almost close to 0, and then concentration of the solids in the D zone is very high. So, from layer to layer as well as with respect to time, this concentration is changing, that is what we understand. So, then this concentration with respect to the settling time we have to find out, and from there the flux with respect to the settling time we have to find out, right. So, then with respect to the time we will be able to calculate flux as well as the concentration of solids at different time intervals. So, that information F versus C we can plot and get the solids flux of that rate limiting layer. Okay. So, it is a quite simple and straightforward, need not to worry, we will be doing some problems also. So, here C is nothing but layer composition, whichever layer we have taken. So, that is the reason we have not designated anywhere C1, C2, CL, Ci, something like that, nothing is being designated, because it is a generalized one. Whichever layer, for whatever the layer you are trying to calculate the flux, for that layer the concentration of the solids in that layer is C, and then V is the settling velocity of the solids at that particular C. We already understood the settling velocity of the particles is a kind of concentration function of the concentration of the solids. Okay. So, Lu is the underflow volumetric rate, whatever the volumetric rate that you are taking through the D zone, the solid sludge that you are taking out through this bottom zone, D zone, that is Lu. Okay. And then A is the cross sectional area normal to the flux. Okay. So, the first term of RHS of the above equation is the flux of the settling particles called the batch flux, that is Cv is nothing but the batch flux, and is obtained from the batch test data. The second term is flux associated with the withdrawal of the solids through the bottom due to underflow, that is known as a kind of underflow flux. Okay. So, now let us say for a given system you already have Z versus theta information, that is in interface, the clear liquid AB interface versus theta information that you are having, right. From there you are able to find out the Cl concentration from C naught Z naught by Zi information for different theta information for different times. So, that means you are able to calculate the concentrations also for different layers, right. Once you have the concentration for different layers, then you are able to generate the flux, batch flux as well as the underflow flux. Let us say that information is completely available, then you plot. So, then when you plot it, the solid flux, whatever the total flux that is there, so that if you plot against the solids concentration in the slurry, so you may have a kind of curve like this, right. So, this is the total flux, right. And then if you draw this underflow flux, so then you may have a straight line like this. So, now you can see there is a region where the flux is minimum, So, the solid flux corresponding to this minimum location is known as the FL, or the solid flux of the rate limiting layer, whichever we have considered, and then corresponding concentration is CL. Sometimes you need to know the underflow sludge concentration also. Sometimes in problems it is available or it is requirement. So, you wanted to collect the sludge at such so and so concentration like that. So, if it is not there, so under this flux, whatever the when this minimum flux is established, under such conditions you start taking the underflow like that. Okay. So, what is the corresponding underflow concentration? If you wanted to know this line, this FL line, if you extend to further in the increasing x direction, so that may be intersecting at this point with the underflow flux, right, and then corresponding concentration whatever is there, that is nothing but Cu. That is nothing but Cu. So, this is what the solid flux versus concentration information, this is what you get it here. So, solids flux Fl at concentration Cl is less than solids flux at other two concentrations C0 and Cu. Whatever the at C0, if you calculate the solids flux, and then whatever the concentration at Cu, if you find out the solid flux, whatever the solid flux are there, they are going to be the they are going to have a kind of higher value of the solid flux compared to the kind of solid flux at this Cl concentration. Therefore, Fl is limiting solid flux capacity and an area must be provided so that flux does not exceed Fl. Therefore, required area for the thickener we can get it as A is equals to L naught C naught by Fl. So, now we can see it is so simple for a continuous thickener. If you able to find out this solid flux of the rate limiting layer, right. So, whatever the limiting solid flux capacity or the solid flux of the rate limiting layer Fl, if you can find out, you do not need any other information to calculate the required area for that particular thickener. Okay. So, because in general L naught C naught are given. L naught is nothing but initial feed slurry inlet, whatever the inlet of the feed slurry we are giving to the continuous thickener. So, in volumetric flow rate, that is L naught, that is L naught. C naught is the initial feed slurry concentration. Initially before sedimentation, what is the concentration of the solids, uniform solids concentration before the start of sedimentation, that C naught is also known. So, Fl if you find out, then directly you can calculate the area using L naught C naught divided by Fl. So, the area calculated from above equation is the minimum area that must be provided for a continuous thickener operating at steady state. Okay. So, now this is what one of the ways to get the area requirement for the thickener, that is the design of a thickener. This is how we do. In general, design of thickener means what? You should able to obtain a kind of required cross sectional area and depth of the container that you are using for a given sedimentation duty. Okay. So, you can fix the depth and then accordingly you can calculate the area. Okay. Now, we go to a different method to get this area of a thickener. How to calculate area of thickener from a different approach we can do, which is quite similar and straightforward as the previous one. So, time and concentration at critical flux. So, use of the above equation, that whatever A is equals to L naught C naught by Fl, this equation whatever is there is straightforward to obtain the area of thickener, right. So, but however, it may be of interest to know at what time and at what concentration this critical flux is realized, right. So, that you can if you can find out, that is going to be a kind of additional information. Indeed, from that additional information also we can calculate the area, required area for a given thickener duty. Okay. So, that we are going to see now. Okay. Remember, whatever the Cl is there, that is not a kind of critical concentration, right. So, what concentration this critical flux is realized, that is what we are going to see. So, the Cl is a kind of a layer that is moving up, right. So, now that is different and this critical flux also different. Okay. So, whatever this critical time or the concentration at critical flux that we are going to calculate, that is the point. From that time onwards, the sedimentation of particle or the settling velocity of particle drastically decreases. Pictorially we will be seeing now here anyway. Okay. So, batch sedimentation is basis for these calculations according to Talmadge and Fitch. So, what we do? We have this height of the interface versus time data, right. You do a batch study, batch sedimentation study, and then get this height versus time information. Okay. So, simply you take a cylindrical column and then you take a initial feed slurry which is having certain C naught concentration, and then with respect to time you find out how this interface is dropping down, right, with respect to time, because obviously as the time progresses solids are settling down. So, then the clear interface liquid is also falling down, right. So, that information Z versus theta, that interface height we call Z, and then time of sedimentation at which we noted that interface height is the theta. So, when you plot it, so you get a curve like this, you get a curve like this. Right. So, now this is the initial Z naught, okay, initial height Z naught, and then let us say the last point Z whatever is there at this point, right. At these 2 points what you do, you draw tangents, like this at these 2 points, that initial Z naught and final data point whatever that you have, you draw tangents like this. So, when you draw this tangent and extend them, so they may be intersecting each other at certain point, and then when they are intersecting they are making some angle, right. This angle if you bisect in 2 equal parts and then draw a kind of angle bisector line like this, and then extend it towards the Z versus theta curve, you just extend it, right. So, this angle bisector line is intercepting this curve at certain point, right. That point is corresponds to critical flux point, and then corresponding time is known as critical time, and then corresponding height is ZC. Okay. So, critical time that you got right now. Okay. So, we can get the critical concentration also. How to get the critical concentration at this point? If you at this theta is equals to theta c, if you draw a tangent that will be intersecting this y axis at z is equals to z1. So, if you wanted to know the settling velocity of the particles at theta is equals to theta c, that should be z1 minus zc divided by theta c, right. So, let us say the settling is occurring from theta c to theta u time, then what should be the settling velocity of those particles? So, the particles in that settling velocity of the particle between these two time zone would be nothing but zc minus zu divided by theta u minus theta c divided by theta u minus theta c, because v is nothing but minus dz by d theta, right. So, how to get this theta u? How to get this theta u? So, that is also important. So, now when you drawn this tangent at theta is equals to theta c, you extend it, and then at final point, whatever the final data point that you have at, let us say, that point D. So, at that point what you do, you draw a kind of horizontal line, right. So, wherever this horizontal line is intersecting on y axis is nothing but zu, right, and then this horizontal line is intersecting with the tangent at theta is equals to theta c. So, the corresponding time is nothing but theta u, that corresponding time is nothing but theta u. Actually, this theta u, that is what we are going to use for area calculation now anyway. So, this is additional information before going for the area calculation. So, this theta u is anyway useful for area calculation, but in addition to that one, when we do this process, we are able to find out critical time and then concentration at critical flux. Okay. So, that we are able to find out through these 2 points, right. Okay. So, what does it mean, the critical flux? So, that is the critical point. What does mean by critical point? Critical point is the point from that point onwards the settling velocity of the particles is drastically decreasing, right. So, let us say from z0 to zc, or from 0 to theta c time, the settling velocity is sufficiently is there. So, after that the settling velocity, change in settling velocity is not that much in general. Okay. So, that is what mean by that point at which the settling velocity is going to decrease drastically is known as the critical point. So, now we try to get the additional information now. Initial uniform feed concentration is C naught, total mass of solids in the cylinder is C naught, A, Z naught, straightforward because A is cross sectional area of the cylinder and Z naught is initial height. Let theta c be the time needed to reach the critical concentration Cc, then practically this concentration is reached at a time when the settling velocity decreases rapidly, right. Then mass of the solids in the cylinder is constant during the entire test, obviously because there is no mass loss. Okay. Material balance on solids, if you do different times, C naught A Z naught is equals to Cc A Zc is equals to Cu A Zu, like that you get it. Okay. Because the total mass of solids is same in the cylinder. So, material balance on solids, if you do at different times, C naught Z naught at the initial point, like before starting the sedimentation, Cc Zc are corresponding to the critical point. At that point also the total number of solids are same, and then same is like at Cu Zu are corresponding to the underflow sludge concentration, right. So, at that point also total solids are same in the system. So, all these things are same. Okay. Only thing like A is fixed here, A naught Z naught, A is fixed here all the cases, C naught Z naught, Cc Zc, Cu Zu are changing in a combination such a way that this total value of product value whatever C naught, A naught, Z naught, Cc A Zc, Cu A Zu are there, that is going to be constant. So, since area is constant, the same equation you can write it as C naught Z naught is equals to Cc Zc is equals to Cu Zu. So, where U denotes underflow values. If the thickening process is thought of as going from Cc to Cu, an amount of water must be removed to accommodate this change in concentration. So, what is that amount of water? So, volume of water that is to be squeezed out is nothing but that cross sectional area A multiplied by the time difference, the height difference, cross sectional area A multiplied by the height difference from Zc to Zu, that is Zc minus Zu. Okay, because we are assuming this rapid change is taking place, the rapid decrease in settling velocity is taking place from theta c onwards. So, theta c to theta u time whatever the corresponding heights are there, interface heights are there, that we should take as a difference Zc minus Zu and multiplied by the area, then you will get the volume of water that is to be squeezed out. Then time required to discharge this volume of water, obviously theta u minus theta c, from graphically we have seen. So, then volumetric flow rate L would be V by theta u minus theta c. So, then we get A into Zc minus Zu divided by theta u minus theta c. Simply by substituting here for V, A is equals to Zc Zu, if you substitute you will get this L, volumetric flow rate. And then solving for this theta u minus theta c, that means A multiplied by Zc minus Zu divided by L, that if you do you will get theta u minus theta c. Settling velocity at theta c is obtained from the slope of the curve at theta c, and then as I already did in the graphical approach there. So, if it is like theta c point, at this point if you draw this intercept, so what happens, it will be intersecting somewhere this y axis, and then that is known as the z1, and then the interface height corresponding to theta c is nothing but zc. So, z1 minus zc divided by theta c, if you do you will get settling velocity at theta c. So, under continuous flow conditions clear liquid upflow cannot exceed Vc if thickening is to occur. So, we do not want these solids to go into the clear liquid, we want the solids to be settled. So, then under the continuous flow conditions, clear liquid upflow should be maintained so that it cannot exceed the Vc if thickening is to occur. Okay. Upflow, whatever the clear liquid overflow that you are taking, its flow rate should be less than the Vc if thickening is to occur, otherwise in that clarified liquid particles will come in, okay, that we do not want. Therefore, flow at theta c when thickening starts is nothing but L is equals to A into Vc. A Vc Z, just now we have seen Z1 minus Zc by theta c, right. So, now substitute L from above equation in equation number 16. This is the equation number 16 that previous slide we have seen. So, when you substitute here, you get Zc minus Zu by theta u minus theta c is equals to Z1 minus Zc divided by theta c. So, above equation you used to calculate theta u from the figure as follows, as I already explained. So, let us say once again we draw this z versus theta information, right. You draw a tangent at z naught, you draw a tangent to this curve at final data point, right. So, they may be intersecting each other at some point, right. So, that angle whatever is there you divide into half and then draw a kind of angle bisector line, something like this. So, that may be intersecting this z versus theta curve at some point. So, that point is corresponding to a critical point, right. Corresponding concentration is Cc, corresponding time is theta c, right. So, now at this point you draw a kind of tangent at theta c and then extend it like this, right. So, at this Zu information that we already calculated, at Zu information what you do, you draw a kind of a horizontal line this thing, and then Zu line constant line, if you horizontal line when you draw, so that is going to intersect this tangent and theta c at some point, and then corresponding time is nothing but theta u, that we have already seen in previous slide also, right. So, then for this we need to know Zu. So, Zu we can calculate Z naught C naught by Cu, because C naught Z naught is equals to Cu Zu is equals to Cc Zc, that is all we have already seen, because the total solids in the system are going to remain constant. So, then equation theta u can be calculated from equation 19 as well. From this equation also you can calculate, or from graphically also you can calculate if you know the Zu, right. So, because in this equation Zc you already calculated, theta c you already calculated, Z1 is nothing but the intercept of tangent at theta is equals to theta c, whatever that Z1 is also known, right. Zc is there. So, Zu if you calculate from here and then substitute here, so theta c is also known, only unknown is theta u, right, only unknown is theta u. So, once again for kind of clarification, because of the symbols, you know what we have a kind of picture once again here, draw a kind of clear picture, bigger ones probably, right. So, these intercepts we have Z versus theta curve we have like this. At this Z naught point and final data point we draw on the the tangent lines, and they are intersecting each other at some point. So, that intersect angle whatever is it, that you bisect it, right, bisect it, and then that point where that when you bisect this line, like extend like line bisector line like this, so that will be intersecting this Z versus theta curve at certain point, right. So, that point is corresponding to theta c, and then corresponding height interface height is Zc, right. So, if you draw a kind of interface like if you draw a kind of tangent at theta is equals to theta c, so that is intercepting this line y axis line at some point, that is Z1. So, that is Z1 is known, Zc is also known, that is what I mean by, if you know the Zu, right? ZU, at that ZU you draw a kind of constant horizontal line like this. So, that line may be intersecting this tangent at theta is equals to theta c, and then corresponding time whatever you get, that is nothing but theta u, right? That is nothing but theta u, and then this point is nothing but theta c. So, everything is known except theta u. So, theta u you can get graphically like this, or in this equation also z1, zc, zu, theta c are known. So, theta u you can calculate from equation number 19 also. So, whatever this information that process that we are doing, that we are doing for a kind of a batch sedimentation test, right. So, information we are getting from the batch sedimentation test only, but however this procedure can also be applied to continuous thickener according to the researchers who developed this method. So, average mass rate at which the layer of concentration Cu forms in the thickener is nothing but Cu Zu A by theta u, obviously, right. So, Cu is the concentration of solids, that layer whatever the underflow that is there, Zu is the corresponding interface height, A is the area, and then theta u is the time required to reach that Zu interface height. Okay. Then since Cu Zu is equals to C naught Z naught, the same average mass rate we can write it as C naught Z naught A by theta u. Why we are doing? Because initially Cu Zu are not known, we are going to obtain by this graphical method. So, however, we try to reduce the work so that we can get the required information with minimum effort, right. So, now here Cu Zu is nothing but C naught Z naught. So, C naught Z naught are known initially from the problem statement. So, that we can write rather writing Cu Zu. So, then average mass rate is nothing but C naught Z naught A by theta u. Then for continuous operation, the rate at which the layer of concentration Cu is formed must equal the rate that at which solids enter the unit, right, because then only steady state conditions will prevail for a given continuous operation. Okay. So, that is the rate at which the layer of concentration Cu is formed, that must be equal to the rate that at which solids enter the unit. So, that means rate at which solids enter the units is nothing but L naught C naught. Okay. So, that L naught C naught should be equal to this C naught Z naught A by theta u. So, this C naught you cancel out, and then from here you can write an expression for A as L naught theta u by Z naught. L naught theta u by Z naught is nothing but the area required for that continuous thickener. Okay. So, now L naught is what? Initial feed rate, whatever the feed rate at particular volumetric rate that is entering to the continuous thickener, that is L naught, and Z naught is nothing but initial interface height. Theta u is nothing but the time required that interface to decrease from Z naught to Zu height. Okay. So, here also straightforward, only one thing is required is theta u. Only one thing is required is theta u. So, this theta u you can get from graphically as by the equation number 19 previous slide that we have seen. Okay. So, here also the area of continuous thickener you can apply, you can obtain by this method. Previous method we required solid flux of rate limiting layer. Here we need the time required to reach initial interface to Zu interface. So, that whatever the time theta u requirement is there. So, that if you know, you can calculate the area of the continuous thickener, right. So, now we see couple of example problems, so that to understand how to use this equation and get the area requirement. Example number 1, batch sedimentation of limestone slurry. So, here the initial concentration C naught is given as 236 gram per liter, Z naught is 36 centimeters. So, obtain Cl versus V from the data set given in the table. So, in the table theta and then Z, this is theta, this is Z, theta versus Z information is given. How the height of the interface is decreasing with different time interval, that is given here. From this information, what we have to do? We have to obtain Cl versus V information, right. So, now we use the first equation that we developed yesterday, that what we have developed, Cl Zi is equals to C naught Z naught. right. So, what we are going to do, we are going to draw this z versus theta information graphically like this. Something like this. So, at each point at different intervals you take like this, different intervals in the time, at each point also you can do. So, you can take around 8 to 10 intervals of time, not necessarily same as like this. So, from the graph, let us say at 2 hours, this is the point at 2 hours or 3 hours, something like that. At this point, if you wanted to know the at this point of sedimentation time, the x axis is nothing but sedimentation time. So, at this point of sedimentation time, if you wanted to know the concentration of that layer, what you do, you draw a kind of tangent like this at this point. So, it may be intersecting somewhere, let us say if it is theta 1. So, then corresponding this one is nothing but z1 and then this is zi. If you wanted to know the velocity, it should be zi minus z1 by theta 1, then that will give the settling velocity. So, V is known. So, then after that C you can calculate, because the zi is also known. So, C naught z naught by zi, if you do, you get the CL information. So, both of the information are known. So, that is just a graphical work that we have to do here. So, solution, that CL is equals to C naught z naught by zi, where zi is the intercept value of the tangent at a given time. So, let us say that data, if you plot, you will get a graph like this, right. So, now what you do, let us say at 2 minutes, of time, you draw a kind of tangent like this. Right. So, let us say this is the point corresponding to theta is equals to 2 hours, not 2 minutes, it is given in 2 hours. So, at 2 hours, if you draw a kind of tangent, right. So, that may be intercepting this y axis at 20 centimeters. So, this zi corresponding to this one is nothing but zi is equals to 20 centimeters. Okay. So, now from here, if you do at this point, if you take the slope of this curve, slope of this tangent whatever that you have taken at this point on the curve at theta is equals to 2 hours, if you take minus dz by d theta, then you will get 2.78 centimeter per hour. So, that is nothing but the settling velocity of the particles at that particular time, right. So, then after that concentration CL, you can find out C naught z naught by zi. C naught is given as 236, z naught is given as 36, zi at this point of time we have got it only as a kind of 20. So, overall CL final information is that 8496 divided by zi, this is what we have. So, now different time intervals, you find out different zi's and then you substitute here. So, you will get with respect to time, this CL information you will get, and then the slope of those tangents at different time intervals, whatever you get, that is nothing but the V information, settling velocity of the particle. So, when you do that one, you will get this one, let us say CL at 2 hours time, zi we already got this as 20. So, 8496 divided by 20, if you do it, it is coming to be something like 425 roughly, right. And then V at this point, dz by d theta at this point, theta is equals to 2 hour, we have already seen it is 2.78, right. Let us say if you do it at 4 hours time, at this point if you draw a kind of tangent like this at this 4 hours point time, like this. So, this here now zi is going to be something like 14.2 centimeters, and then minus dz by d theta of this line at theta is equals to 4 hours is nothing but 0.646 centimeter per hour, and then CL for this time is nothing but it is going to be 8496 divided by zi is 14.2. So, that is roughly coming out to be 600 gram per liters. Okay. So, This is how we can get we can construct C versus V information. Okay. Now we take another example problem. Using the data set of example 1, determine the area and underflow flux at underflow concentration of 700 gram per liter with underflow velocity of 500 centimeter per day, something like that. So then given data is feed rate L naught is given, initial feed rate entering this slurry, at what rate it is entering this continuous thickener, that is given, L naught is given in liters per day. Feed concentration, that is C naught is given, the same as the previous problem, that is 236 gram per liter, and sludge concentration here it is given, Cu is given, that is 700 gram per liter, that is taken as a kind of underflow, and then Vu is also given, and then Vu is also given, that is underflow velocity is also given 500 centimeter per day. So that means underflow flux you can directly calculate easily here. Okay. So that now what we do, you need to have a kind of consistency of units, day, liters, centimeters, different units are there. You should be very careful about these units. Okay. So now solution steps, area, because now here flux are required. The part of the question is that you have to determine the area and then underflow flux, right. So the flux calculations, if you do, whatever the limiting layer flux FL is there, once you get that, you substitute here L naught C naught by FL, then you will get the area requirement. So FL we need to calculate. So total flux F is equals to FB plus FU. FB is nothing but C into V. C for different times, V for different times, at different theta values. We have already done in the previous example problem 1. So from there we can get, that means FU is nothing but multiplication of whatever the C and V columns of a previous example, whatever the C and V information that we got as a kind of solution of the previous problem. Okay. And then FU is nothing but C into VU. It is not CU into VU, it is C into VU. So then at different times C, that also we have already got it here, okay, in the previous problem. So that C, if you multiply it by V, then you will get FU. So now flux we wanted to have in gram per centimeter square hour. So the liters whatever is there, 1 by 1000 we have done. So then liters are also converted into the centimeter cube, right. And then here centimeter per day VU. So what we have done, divided by 24, so that it is come into the centimeters per hour. So that overall these units are going to be gram per centimeter square hour. So what we have to do, first step, whatever the FU, FB values we have to calculate it. We have to calculate. FB value is straightforward, is the nothing but the solution of previous example problem. C and V are the solution of previous example problem, or C versus V information for different time values is a kind of a solution for the previous problem that we already got. You just simply multiply those values, two values for different times. So then for different times FB you will get it, right. Similarly, at different times concentration, solids concentration we know that if you multiply it by VU, then you will get the underflow flux. Then when you add them together, you may get a kind of something like a total flux, whatever required flux. So this time, Zi, C, VL, these four are adopted from the previous problem, because it is a continuous of the previous problem. This we have already done. Then now here this FB is nothing but C into V. So this 236 multiplied by 15.7 if you do, that comes out to be 3705.2, something like that. That would be in liters. So but we have to convert this one liters as a kind of in terms of centimeter cube. So then if you divide by 1000, you will get 3.7052 gram per centimeter square hour as a kind of batch flux. And then corresponding flux here, underflow flux is nothing but C multiplied by VU. So 236 multiplied by VU information for the first case, this is 236 multiplied by 0.0 to 0.8, if you do, you will get 4.9088 gram per centimeter square hour. You should be careful about these units, because this units for concentration is given in gram per liter and then flux is in gram per centimeter square per hour. Okay. So, total flux would be the addition of these two. Like that, for other time values also you calculate the batch flux, underflow flux and then total flux. So, total solid flux you can get it. This total solid flux, if you plot F versus concentration, then you will have this kind of curve. We may not have exactly the similar nature of the curve, because it is a kind of ideal condition I have shown like this. If you plot like this, you may have something like this, something like this, and then underflow flux, if you draw like this, you will have like this. Okay. So, the corresponding to the point where the minimum flux is there, right, there would be some point where the flux would be the minimum, right. The lowest flux point, that is nothing but the rate limiting layer solid flux, or the solid flux of the rate limiting layer FL, right. So, that FL you simply substitute, and then here in this case you will get as 15.5 gram per centimeter square hour. Okay. So, simply area is going to be L naught C naught by FL. So, that is going to be 3.24 into 10 power 6 centimeter square. So, this is the minimum area required for the continuous thickener, which has to perform this duty according to whatever the Cu, Vu, etc. are given. Okay. Now, we take another example problem. That problem will be calculating the critical time, etc. That approach we follow, and then we obtain the required area for a continuous thickener. Calculate the area of a continuous thickener to treat a biological sludge. Given data, C naught is given, Cu is given, L naught is given. Calculate the area of the thickener. Right. Here Vu is not given. Right. If Vu is not given, so then you cannot obtain the underflow flux. So, the flux method you cannot use for this problem. You will not be able to solve, because Vu is not given. Cu is given, but Vu is not given. If had it been given, so then this problem could also been solved as a kind of example number 2. Since it is not given here, so underflow flux Fu you cannot calculate. So, solid flux versus concentration plot, from there getting FL and then getting A as L naught C naught by FL is not going to be possible. So, what we have to do? We have to find out theta u and then use the critical time approach to get this area requirement. Okay. So, the data time versus interface height is given in time is given in minutes, and then interface height is given in centimeters. So, first what we have to do? We have to plot z versus theta. Z versus theta you have to plot, and then two ends of data points are z is equals to 51 centimeters and then z is equals to 10.7 centimeters. So, z naught is 51 centimeters as per this data points given. Z naught is nothing but 51 centimeters, right, because it is at 0 time. Okay. So, at the last data point, that is at 10.7, and at this first data point at z is equals to 51. At these 2 points we have to draw two tangents to this z versus theta curve like this. So, this is z naught point, this is let us say whatever the 10.7 point or something like that. At these 2 points you draw a kind of tangent like this, which we have already done, something like this, right. So, and then extend this tangent so that they intersect. So, when they may be intersecting at certain angle, so that angle you divide into 2 equals and then draw a kind of a angle bisector line like this and extend it towards the z versus theta curve. So, this angle bisector line is intercepting this curve at certain point, that point is corresponding to critical concentration or critical point, then time is known as a kind of a critical time, right. So, the corresponding interface height is ZC. At this point, at theta is equals to theta c, now again you draw a kind of a tangent like this, and then this tangent at theta is equals to theta c is intercepting y axis at z1. Okay, right. So, but we need theta u, we need theta u information, right. Zu is given here in the problem, Zu is not given here, right. So, we will see anyway. So, by doing this one we get theta c as 6.5 minutes, and then Zc is something approximately 20 centimeters that we get here. Now, when you draw tangent at theta c, then Z1 we get it as a kind of 32.5 centimeters as a Z1 kind of thing. And then Zu we need to find out, Zu is nothing but, it is not given, so we have to find out, that is nothing but C naught Z naught divided by Cu. When you do it, you will get 11.7 centimeters. So, equation number 19 we can use to get theta u information, because theta u is the required information in order to get the area. That way you can do, or graphically also you can do. At Zu is equals to 11.7 centimeters, you draw a kind of horizontal line like this, and then this line may be intersecting with the tangent at theta is equals to theta c at certain point, and then corresponding time is nothing but theta u, and then here that comes out to be 11.2 centimeters. So, that is it. Area you can calculate it, area you can calculate it as L naught theta u by Z naught, that comes out to be 6.92 into 10 power 5 centimeter square. Okay. This is how you can calculate the required area of a continuous thickener using either of the approaches. So, the references, we have several references for this course. Okay. So, all of these references are going to be very important, and then all of them must be having some amount of information about these topics that we have discussed in this lecture, but especially this is the new reference I have added. So, this is a very good book for this thickener design, whatever the thickener design and then problems that we have solved. So, those things some material we can find out from this reference book. Thank you.